Okay, so let's get started. Hello, everyone. My name is Sunny Jung. I'm a professor at Cornell University and also associate editor of the Journal of Physical Review Fluid. And I'm so pleased to moderate today's journal clubs. So just quick reminder about the format of this journal club. So we are going to have about 15 minutes presentation of research. And during that presentation, please ensure you are stay muted. But feel free to write down any questions or comment in the chat. And after 15 minutes presentation, we will take questions from the audience. You can either use the chat or raise your electronic hand. Okay. So our guest speaker is Alec Menzer from Harvard University, but he was previously at the University of Virginia. He published excellent, fascinating work in the Physical Review Fluid in April, entitled "The Fish Schools in a Vertical Diamond Formation: Effect of the Vertical Spacing on Hydrodynamic Interactions." So without further ado, please welcome the Dr. Alec Menzer.
Not doctor, sorry.
Again, Mr. Again.
I
Yeah.
haven't graduated yet. But yeah, thank you for the introduction. I'm really happy that APS is putting on this event, and I'm thankful that they invited me to give this talk and are running such a great series for the Journal Club. And like Dr. Jung mentioned, I'll be giving the talk on the paper that I published in April with my collaborators, Yupan and George Lauder at Harvard, and my advisor, Habo Dong at UVA. So to start, just want to give a background, an introduction as to what are the motivations for studying this schooling problem to begin with. So from a standpoint of the ecological system, there's known to be some mating and protection and foraging advantages for these schooling formations. But as engineers, we're primarily concerned with studying if there's hydrodynamic benefits. And there's many hypotheses that exist regarding how fish can school together to increase their thrust, reduce their drag, and as a result, save their energy while swimming long distances. So there's many examples of schooling benefits or schooling examples in, for example, the wild or in many aquariums that are around the world. And when we're thinking about vertical formations, from the biological experiments, the existence of formations where fish are arranged vertical relative to each other are quite common. However, much of the research on the schooling formations from a hydrodynamic perspective consistently make the assumption that the formations exist primarily in the horizontal plane, so horizontal planar formations. But the experiments, biologically, they suggest that vertical formations are very common. So in a recent paper, does a really good job of explaining this. Hung-Teng Ko, who I've worked with on some of our research projects, he's a incoming professor at Tufts University. They did some long duration experiments on the formations of schools, and actually the horizontal planar formations are relatively infrequent. And in comparison, the vertical formations, for example, this ladder, comprised nearly 80% of the total duration of the schooling experiments. These fish were sort of arranged in this ladder formation for most of the time. And despite the fact that, now we're starting to get a better understanding of that this vertical formation is common, it's really not clear, like, what are the flow physics in these arrangements. So there's some work from Yupan, who's at a postdoc at Harvard right now, on the interactions of these two vertically stacked fish, where we know that the thrust can be increased, but when we add the body of the fish, this vertical formation is pretty detrimental to the drag and the power consumption of the system. And this is due to some harmful interactions between the two close-by bodies. And so right now it's still unclear how the vertical formation can be utilized by fish to improve their hydrodynamic performance, or if the vertical formation can be used to improve the hydrodynamic performance. And this close vertical formation yields a lot of interesting potential findings related to the interactions that these fish can leverage. For example, interactions between close-by fins constituting fin-fin interactions, the interactions between upstream generated wakes and downstream fish constituting wake-body interactions, to give just a few examples. So some of our objectives, like I had mentioned, a lot of the research that's been done on fish schooling has focused primarily on horizontal planar formations. And in particular, the horizontal planar diamond has sort of emerged as one of the benchmark formations for studying the kinds of interactions that fish can utilize for benefits in a schooling environment. Dating back as far as 1973, Danny Bayes looked at this sort of leader left, right, follower formation where a leader is flanked by three fish in this like diamond configuration to look at various different effects related to the channeling effect, for example. And some other work recently has looked at this leader left, right, follower formation too in a much denser configuration to understand the wake body and body-to-body interactions. But up to this point, the vertical diamond or diamonds in the vertical plane have not received much research interest, despite the fact that in the horizontal plane, this diamond formation has really served as a benchmark for studying the interactions. The diamond has not been leveraged in the vertical plane for this same reason. But just like the planar diamond, we have a similar formation. For example, we have a leader fish, which is flanked by three downstream fish. The only really change here is that there's a top and bottom position rather than a left and a right. And this video is in the supplementary materials of the paper taken at the Lauder Lab at Harvard. And just like this, how this horizontal planar diamond is really used to study the formations in the horizontal plane, the main question that we hope to answer is, are there hydrodynamic benefits? And if so, what are the hydrodynamic interactions that are responsible for this performance change of fish in vertical diamonds? So to study this sort of vertical diamond formation, we look to the experimental videos to get an inspiration of how the vertical diamond might look. And so just like I mentioned for the horizontal planar diamond, we have a leader fish flanked by three downstream fish, the top, the bottom, and the follower. And this formation, just like in the planar formation, is controlled by the streamwise distance and the vertical stack height, analogous to the lateral spacing between the left and the right fish. And we're mainly concerned right now with changing the vertical stacked height because still as of yet, the effect of these vertical spacings on the hydrodynamic interactions in schools is not yet well understood. So our main focus is to understand the effect of this vertical height on the interactions. And by changing this vertical height, we hope to extract some information about the changes in the wake interactions and performance changes. And as fluid dynamicists, we also want to know, are these interactions, if any, relevant across a range of Reynolds numbers and including biologically relevant Struhel number or Reynolds numbers for these giant danio fish that we're studying in this work. This is the computational model of a giant danio. And in laboratory experiments, they reach in their sort of more relaxed swimming scenarios, Reynolds numbers between 6,000 to 10,000. So these are relevant Reynolds numbers for the giant danios at the higher end of the spectrum. But the main analysis occurs at a Reynolds number of 4,000. So for the numerical methods, for these bio-inspired problems, it's difficult to sort of accurately simulate the problem for this really complex and arbitrary geometry. So we implement a sharp interface to immerse boundary method, which uses non-conformal Cartesian background fluid grids and uses the immerse boundary method to accurately impose the boundary conditions of this irregular body on a Cartesian grid. And to further improve the efficiency of this calculations, we use a tree topological mesh refinement technique where we can efficiently, in a parallelizable method, solve the governing fluids equations, which are the incompressible Navier-Stokes equations, on these layers and blocks that we sort of partition the domain up into. And using this technique, we reach a very fine grid resolution within the innermost layer of 3/1000th of a body length being the grid size. So this was sufficient for resolving the flow features and the forces at the Reynolds number that we've selected. So now I want to move on to the performance of the vertical diamond. So mainly here, what we're looking at is the performance of thrust. So the thrust is the generation of forces by a caudal fin on each of the fish. And what we find is that the top fish, the bottom fish, and the follower fish all receive a major thrust increase, more than 5%, in this denser vertical diamond, where the vertical spacing is much, much smaller. And of course, the leader fish is extracting a smaller benefit than the rest of the fish, but it's notable that it is still a more than 3% increase for this fish here. And looking towards the drag, with decreasing vertical spacing, there's a major drag decrease experienced by the follower fish, while the top and the bottom fish are less impacted. So in this sort of second vertical diamond that I've labeled VD2, which is the smaller vertical spacing, the drag is decreased by more than 15%. So this is really helping us to sort of motivate and understand how are we going to analyze this problem. And what we want to focus on is what is responsible for these large force changes that are causing high thrust on the caudal fins of the top and the bottom fish, and really low drag on this follower fish. So looking at the fin, the fin body, and the wake fin interaction in these schools. So when we look at the differences in the wake formation, one thing that really jumps out towards anyone is sort of difference in the trajectory of the vortex rings, where we see that there's this vertical compression of the vortices around the body of the follower fish. And because these top and the bottom fish are closer together, the vortices generated by the leader sort of overlap with the heads of the top and the bottom fish. So if we sort of look at the regions of interest for this, in region 1, we see that there's this overlap of the leader's vortices with the head of the top and the bottom fish. In region 2, we see that there's this sort of really closely packed caudal fin arrangement where the follower is just downstream of this, and the compressed vortices eventually interact with the caudal fin of the follower fish. So we're really concerned with understanding how this leader stacked fish interaction is improved in the lower vertical spacing vertical diamond. And we're also concerned with how this span-wise compression of vortices is impacting the drag and the thrust of the follower fish. So how do these complex wake structures first interact with the head of the follower fish? So we can see that these two vortex rings that are formed by the top and the bottom fish really hug the body of the follower fish on both the left and the right sides. And as they convex further downstream, they sort of compress around the caudal fin of the follower fish. So we also want to understand how this wake fin interaction is facilitated and improves the thrust. So these are the three main vectors we're going to pursue through the rest of the presentation. So for this wake stacked fish interaction, what we're mainly looking at is the drag of the top and the bottom fish, which did decrease just a little bit in the second vertical diamond with low vertical spacing. So in previous studies, this really dense vertical stack actually increased the drag of these fish. But here we're finding that actually the leader fish's wake is much more capable of improving the drag when these fish are close together. And this leader fish's wake low pressure is counteracting any of the pressure that builds up in front of the fish and actually produces a pretty strong drag reduction periodically as the wakes are passing both between and directly alongside these fish. And here we're looking at what's responsible for the thrust increase of the top and the bottom fish. And this is also related to some work done by Yupon in his PhD dissertation. Here we're finding that when these two fish are really close together, the caudal fins, when they're flapping from left to right, for example, here, these leading edge vortices are very close together in the vertical direction. And so these oppositely signed vortex regions are generating a strong jet between them, which is increasing the velocity gradient and in turn increasing the circulation and the strength of these leading edge vortices, which is directly responsible for the thrust of these two fish. So these stronger wakes are generated because the smaller vertical spacing is able to improve the fin-fin interaction of these fish. As these enhanced vortices generated by the top and the bottom fish travel downstream, of course, the forces and the pressure distribution of these vortices is greatly impacted. So here we're looking at the follower fish drag reduction. In vertical diamond 1, where the two fish are sort of further apart vertically, these vortices, which are the very dark blue regions right on the caudal fin at this time instance here, they're pretty far apart and the pressure gradient is not as high. You can see that the regions of low pressure are less intense than on the right, where these enhanced vortices on the interior of the vertical diamond are generated and enhanced through fin-fin interaction of the top and the bottom fish. And furthermore, these vortices are also very close to the follower fish's body, so we can see that their impact on the pressure force is much greater. So if we look at the pressure force vectors on the bottom half of the screen, we see that in BB1, the pressure force vectors are relatively weak in magnitude, whereas in vertical diamond 2, because of the fact that these vortices are enhanced by the fin-fin interaction of the top and the bottom fish, and also because the vertical distance between the vortices and the follower is lower, the pressure force can be much more oriented in the upstream direction as opposed to the vertical diamond one. So not only are we getting anterior positive pressure annihilation just because of the fact that these vortices are so close to the follower's body, we're also getting a lot stronger suction force on the lateral surfaces of the fish body. So these are both improving the drag of the follower fish. But something that was really interesting about this formation is that actually the pressure drag reduction occurs as well as a shear force reduction. So the shear drag experienced by the follower fish is much lower than that of solitary swimming, which is very surprising. And actually, we find that in this very dense vertical formation, vertical diamond one, excuse me, these are actually reversed. So vertical diamond two should be the top icon, vertical diamond one should be the bottom. Here we see in vertical diamond one, there's this sort of local drag wake generated right where the anal fin of the top fish and dorsal fin of the bottom fish are sort of meeting each other. So these two median fins, those are drag producing structures. And as a result of those fin-fin interactions, this local drag wake is extending downstream to interact with the body of the follower fish. And actually it lowers the free stream velocity that's experienced by the follower fish, which in turn is helping to reduce its shear drag. So, there's a sort of a dual contribution of the pressure force via vortex body interaction, and also the local drag wake formed between these top and bottom fish in the lower vertical spacing diamond formation. And finally, we turn towards the back of the follower fish, having identified that there's an enhanced wake body interaction between the top fish, the bottom fish, and the follower fish. Now we want to figure out how are these compressed vortices interacting with the caudal fin of the follower fish. And we already saw how they were compressed around the body and sort of were on a trajectory to meet the follower fish's caudal fin as they were compressing in the spanwise direction. And here we identify a very complex array of vortices in which the connecting vortex, which is sort of bridging between the left stroke vortex rings and right stroke vortex rings of the top and the bottom fish, they're positioned directly above the forming leading edge vortex. And you'll notice that the sign of the vorticity is opposite. And so this is forming a very strong lateral velocity jet, which is sort of feeding the strength of the leading edge vortex early in this half stroke motion. And so we can compare the size of the leading edge vortex in this early periods of the half stroke, for example, this time instant. The leading edge vortex is already forming. And also the connecting vortex is sort of interacting with the dorsal fin vortex to sort of directly position it alongside the growing leading edge vortex. And this is helping to position the vortex better for an interaction of opposite sign vorticity regions, generating a stronger velocity jet, which is improving the circulation very early in the half stroke. And we can see that compared to the follower fish and the sparser vertical diamond, the follower fish in the very dense vertical diamond has much more accelerated leading edge vortex growth. And so here we're just looking generally at the Reynolds number effects, and we find that across a wide range of Reynolds numbers, the thrust is enhanced in vertical diamond one compared to solitary swimming. And so we can find a lot of the same interactions of fin-fin vortices and the wake-fin vortices here. And finally, we're looking at the drag, and the drag reduction is also apparent across a range of Reynolds numbers, including the biologically relevant Reynolds number of 8,000. And we can look towards the pressure distributions and find that these low pressure regions that we identified in the original study are present in the higher Reynolds number cases of 6,000 and 8,000. And so here, for the vertical diamond interactions, we find that the benefits are sort of distributed across the school within denser vertical diamonds, and it's all related to the decrease in the vertical spacing. So the decrease in the vertical spacing allows the stacked top and bottom fish to counteract the pressure buildup that would otherwise occur without a leader fish, and this helps to reduce the drag acting on these two fish. Also, as a result of this lower vertical spacing, the fin-fin interactions are improving the thrust of these two fish by more than 5%. And these fin-fin interactions are producing enhanced vortices, which is leading to a wake body interaction with the follower fish, reducing its drag by more than 15%. So there's a dual effect of this lower vertical spacing of a vortex body interaction that is benefiting the follower. And also it's reducing the pressure in front of the follower fish too. And finally, as a result of this lower vertical spacing, we get this really complicated vortex interaction where the spanwise vortices are sort of compressing towards the caudal fin of the follower, leading to a vorticity exploitation mechanism that's enhancing sort of the overall thrust of the follower fish as well, increasing its thrust by more than 5%. So finally, I'd like to just acknowledge the UVA Research Computing for their resources on the robotic cluster, and also ONR and UVA grants for the financial support. And with that, I'll open up the question session. I guess I was a little long, sorry, but I'll open up the questions now.
All right, it's great. Pretty nice talk. If you have any questions, please feel free to type in the chat, or you can raise your electronic hand and then you can unmute and you can ask questions. Okay, probably since people need more time to the warm up, so I will ask the first question.
Yep.
So yeah, it's great studies you did. So one question, what is the effect of the body shape? So maybe some fish is more like a fat on the lateral direction, some fish is very
Yep.
slender. So I mean, you look at only one kind of specific fish species, but can you comment like what would be trend would be? More they like
Yeah.
form the diamond shape if they're more slender fish versus the more
Yes.
fish, yeah.
Yeah. Yeah, that's a great question. So we have looked at sort of the effect of the body shape in this sort of diamond formation. So we've looked at, for example, like rainbow trout or tunas. And actually, although the magnitude of the change, for example, the magnitude of change of thrust or drag is obviously not going to be the same based on the change of the body shape. But we do find that there's a lot of the same mechanisms that do result in a performance change. For example, when we have like rainbow trout, which have, like you were mentioning, they have a fatter head. The danios are much more slender, but the rainbow trout have a fatter head. So do the tunas. They can still extract the wake-body interaction. The follower fish is still gaining a sort of a drag reduction as a result of the interaction with the top and the bottom fish. Yeah.
Good. So there are three questions on the chat.
Oh,
I'm
yeah.
gonna go over and then you can.
Should I open them or?
It should be the Ali, or I can read off. The Ali Karimi
Okay.
asked about can the pressure difference between two vertically aligned fish in a fluid generate a propulsive hydrodynamic interaction between them? So there's a question.
Yeah. Yeah. So for the vertically, so for this, the hydrodynamic, sorry, for this, the fish are all constrained to remain in the same positions. And we're mainly just benchmarking the forces that are experienced by these fish. But those vertically stacked fish, they do actually tend to be not repelled, but attracted towards each other because there's a lowered pressure region in between these two fish. And right now, some of the work that we're doing is looking at the like how to station hold in these kinds of like vertical formations. So it would generate a attractive force between them, yes, but we're hoping to understand the stability and the free swimming nature of these formations as well.
And next question, maybe it's a little bit biological question. So what determines the rank, leader versus follower? Yeah.
Mainly, I would say from a fluids perspective, whoever is experiencing the incoming flow first. So typically in the diamond formation, the leader is getting the least benefit. It's sort of like generating the flow disturbances that can be like extracted for benefit by downstream fish. So mainly whichever fish is sort of at the front of the pack, like getting the least amount of hydrodynamic benefit and sort of putting in a lot of the legwork for the downstream fish. In this case, the leader fish is very clearly identified as the one upstream fish. But yeah.
And next, Ronan Gisler.
Yeah.
So, could you comment on the effect of flapping synchronization on these benefits?
Yes.
Yeah, did
This
you
is a great
really
question.
assume
Yeah.
the synchrony? Yeah.
Yes, this is a great question. So, um, for these simulations, we do assume that the fish are all synchronized in terms of their phase of flapping. And some of the current research that we're working on is, so if we were to have, for example, a non-in-phase interaction between these fish that are vertically arranged or even just arranged in general, what is the effect on performance? And we're still working on like answering these kinds of questions, but there are some works that sort of study, for example, we have a fixed streamline spacing, and very frequently the streamline spacing and the phase of the fish are very related to each other in a spatial phase relationship. So if we were to have the fish that are not flapping in phase with each other, right now we do recommend, for example, if they were not flapping in phase, we would sort of change the streamline's positions to ensure that the vortex is intercepted by the body at the correct time according to the new phase that is adopted by the fish. But for this study, we simply assumed that they're all flapping in phase because we just wanted to provide a simple environment to vary the vertical spacing and really study the hydrodynamic interactions. Later on, looking towards randomization or non-in-phase interactions to even better understand the problem.
Okay. All right, so next question, Narayan Kumar, which type of software you use for simulation? Is it
I
rent
see.
equation you solve or something else to estimate drag force?
Yeah, so this is solving the full incompressible Navier-Stokes equations using an in-house developed solver. It's based a merge boundary method based solver, so applying the boundary conditions of these non-conform, like these highly irregular fish bodies. And we're using the merge boundary method to apply the boundary conditions to a fluid grid that's fully body non-conformal Cartesian grid. And for estimating the drag force, we're directly computing. So when we're computing forces, we're integrating the pressure force and the shear force across each of the fish bodies. And for the drag force, the trunk is mainly considered to be a drag-producing structure for the fish swimming, whereas the fin, the caudal fin at the back, is producing more than 75 to 80% of the forward thrust force. So when we integrate the forces across the trunk, and the dorsal fins and the anal fins, we're classifying that as drag. So we're directly computing the fluid forces, and that's how we're computing drag. There's no estimation of forces for this work.
Mm. And he also asked, is your fish fixed while the fluid in motion?
Yeah, so the fish are fixed in their positions, and we sort of initialize the simulations with the incoming flow. Yes, the fish are fixed and the fluid is moving past them.
Okay. So next question, Angelo Ledesma. Is
Mhm.
there optimal horizontal distance between the leader and follower to minimize the energy of motion of follower? So
Yeah, this is a great question. So what in this, so we haven't really directly studied this for the vertical formation, but I think there's a lot of work on the inline planar swimming that we turn to when we like sort of think about this question. And the when we have like, for example, two inline fish swimming together, the greatest benefit can be extracted at typically the lowest streamline spacing where the distance between the fish is typically smallest. The further downstream you go, these vortices are sort of advecting not just downstream, but off to the left and to the right. And so the amount of benefit that can be extracted from a vortex is dropping off considerably the further away it is from you laterally. And so your best chance of extracting a hydrodynamic benefit from some vortex structures is if it's like directly alongside you with the least of the lateral distance. So I do predict that the lower the streamwise distance, the better. But we think, even for longer streamwise distances, it may still be possible to extract a benefit, just lesser in magnitude.
okay. Okay, so next question is by Lin Fu. Did you consider turbulence in the near body region in the high Reynolds number cases? Turbulence may play a role in the drag generation. By the Lin Fu is the committee of the Journal Club. He was behind the scene. Yeah.
Yep, yeah, I received many emails.
Yeah.
Yeah, that's a good question. So for the high Reynolds number cases, we had to greatly increase the density of the meshes near the fish bodies. So um, whereas most of the study was conducted at a Reynolds number of 4,000, for the high Reynolds number cases, for example, Reynolds number 8,000, the grid density was reduced considerably in order to be able to resolve like the near body structures and the forces and things. Um, that being said, the incoming flow was still laminar, and so all of the unsteadiness in the flow structures was just uh, dependent on the vortices produced by the fish and not based on some like energy cascade in the flow around it. So we didn't consider turbulence in that effect, but I hope that answers your question. We didn't really consider the turbulence as in this study.
Okay, all right. So I think we just passed the 11:30 in the Eastern time. So thanks, speaker Alec Menzer again. So also thanks everyone for joining today's seminar. We look forward to seeing you all again in the next journal club. Just keep in tune. Okay, and have a great rest of the day. All right, thanks.